Majority element. Have you ever stared at an array and wondered which value silently dominates the room? Majority element is a Pattern Mastery 100 essential and a favorite warm-up at Fong screens. Mastering it proves you can turn raw iteration into sharp insight with O1 space. Today we'll crush it using the basic framework and the legendary Boyer-Moore voting trick. Fast, elegant, unforgettable. Breakdown. We're given an integer array and guaranteed there's a majority element, a value that appears more than n/2 times. Our task: return that element. Because a strict majority exists, it must be the final winner if we pair off different elements until one remains. Assess. A hash map count would work in ON time but ON space. We can do better. Boyer-Moore voting runs in ON time and O1 space by tracking a running candidate and a count. When we see the same value, we vote +1. A different value votes -1. Whenever the count drops to 0, we switch candidates. With a guaranteed majority, the final candidate is the answer. Structure. Plan. Initialize candidate equals none, count equals 0. Iterate through the array. If count equals 0, set candidate to the current number. If current equals candidate, increment count, otherwise decrement. At the end, return candidate. If the problem didn't guarantee a majority, we'd re-verify by counting, but here it's guaranteed. Solution 1. Hash map count time complexity. ON. We begin by defining a class called solution. This is simply a container for our method. This defines our function majority element, which aims to find the number that appears more than half the time in the list. This majority element is guaranteed to exist. We create an empty dictionary called counts. This will keep track of how many times each number appears, like a scoreboard. We loop through every number in the list. This loop runs n times ON. Here's where we count. Counts.getNum, 0, means give me the current count for this number. If it doesn't exist, use 0. Then we add 1 to update its count. We're updating the scoreboard entry for each number we see. After updating the count of the current number, we check if it's now the majority. If the count exceeds half the size of the list, that means this number must be the majority element. And if we find such a number, we return it immediately. No need to keep scanning. Final wrap-up. And that's how this algorithm works. It first sets up a dictionary to track counts, then scans once through the list, updating counts and returning the first number that crosses the majority threshold. Efficient, simple, and elegant. Test case check. Majority element, hash map counting. Let's test our function using this input. 3, 2, 3. This array represents a list of numbers, and our goal is to find the majority element, the value that appears more than half the time. Here's why the solution works. We build a running count for each number using a hash map. As soon as any number's count becomes greater than n/2, we return it immediately, because by definition, that number must be the majority. And that's exactly what our program outputs. 3. It matches the expected majority element perfectly. Wrap up. So, our implementation is correct. The algorithm successfully identifies the element that appears more than half the time. Simple, efficient, and accurate. Solution 2. Boyer-Moore voting algorithm time complexity. ON. We start by defining a class named solution. It simply organizes our algorithm neatly in one place. This defines our function majority element, which finds the number that appears more than half the time in the list. The Boyer-Moore voting algorithm does this in a brilliantly efficient way. We create a variable called count, starting at 0. Think of this as our vote balance. As we scan through the list, this number will go up or down depending on which value we see. We also create a candidate, which is the number we currently believe might be the majority element. At the start, we haven't chosen anyone yet, so it's set to none. We loop through each number in the input list. This is a single pass, giving us a time complexity of ON. If our vote count drops to 0, that means our current candidate has been balanced out by other numbers. So we need to choose a new candidate. We set the new candidate to the current number we're looking at. This number now becomes our new majority contender. This is the heart of the algorithm. If the current number matches our candidate, we add a vote by increasing count by 1. If it does not match, we subtract a vote by decreasing count by 1. In simple terms, matching the candidate strengthens it, different numbers weaken it. The true majority element will survive all these vote battles. Finally, after one full pass, the surviving candidate must be the majority element, so we return it. Final wrap-up. And that's how this algorithm works. It first tracks a candidate and a running vote count, then adjusts that count as it scans, allowing the true majority to naturally rise to the top. Efficient, simple, and elegant. Test case check. Majority element, Boyer-Moore voting algorithm. Let's test our function using this input. 2, 2, 1, 1. 1, 2, 2. These numbers represent a list where one value appears more than half the time. Our job is to identify that majority element. Here's why the Boyer-Moore algorithm works. We keep a running candidate and a count. When the count drops to 0, we switch the candidate to the current number. Then, for each element, we add to the count if it matches the candidate or subtract if it doesn't. And that's exactly what our program outputs, too. It matches the expected value perfectly, proving the voting algorithm worked as intended. Wrap up. So, our implementation is correct. The algorithm successfully narrows down the majority element using constant space and a single pass, efficient, accurate, and reliable. Majority element. Let's do a recap. Ever face a problem where one number seems to quietly take over the whole array? Majority element is that test of insight, a simple setup that exposes whether you can think beyond counting and find patterns in balance and dominance. Breakdown recap. Conceptually, we're finding the element that appears more than half the time in an array. Because that majority always outnumbers the rest, even if we cancel out every pair of different elements, the true majority will still remain in the end. Assess recap. We compared two main approaches, using a hash map for frequency counting versus the Boyer-Moore voting algorithm. Both run in ON time, but Boyer-Moore uses just O1 space, elegant, efficient, and the clear interview favorite. It tracks a candidate and a count, adjusting as elements vote for or against it. Structure recap. We structured it around one simple rule. When the count hits 0, pick a new candidate. If the current number matches it, increase the count, otherwise, decrease it. By the end, the guaranteed majority remains as the final candidate, no second pass needed. Implement recap. We ran the logic step by step in LeetCode, and it executed perfectly. No errors, no extra space, just clean, consistent majority detection. Check recap. All test cases passed. The algorithm correctly identified the majority element across different arrays, confirming that our approach worked exactly as expected. Closing insight. The takeaway? Majority element teaches one of the most elegant uses of mathematical balance in algorithms. Once you understand how to cancel out competing values, you'll start spotting similar patterns in many optimization and voting problems. Fast, clean, and interview proven.